Ahoy, Captain! There's a ship off the starboard bow! Hey everybody, welcome to this week's walkthrough. We're going to be going over optical instruments, and we're going to talk about the different combinations of lenses that can be used for looking at things close and far away. But before we get into all the details, let's talk about this week's PreLab activity.
To perform this week's PreLab activity is fairly straightforward. You navigate to the website that's given to you by your TA or on D2L or in the PreLab guide, and you'll navigate to this page. This is simply a simulator for two lenses, and what you have is movable parts. Which you grab this circle here, you can move the object both in height and position. You can readjust the focal length of the first lens or of the second lens. And finally, you can adjust the position of your second lens relative to the first lens. This is going to remain fixed at 0. You can't move it around as much as you may want to. And so what you'll do is you'll manipulate your position of your object. You'll manipulate the focal length according to the instructions in the PreLab guide. And then you'll screenshot this image, transfer it over to a Word document, and then submit that. And that's pretty much it for this week's PreLab.
The key for lenses in combination is fairly straightforward. What you're looking for is every time you create an image from one lens, it becomes the object for a second lens. So in this case, in this demonstration here, which we have set up as a microscope configuration has a lens with a short focal length and an object just close but outside that focal length. And you do the 3-ray diagram that you did before for a single lens. So you have your first ray goes horizontal, parallel to your principal axis, and it refracts at your lens, the center of your lens, and then down towards the focal point on the opposite side, comes down through. For your second beam, it's going to come down through the same side, focal length again, and this time it's going to refract straight. And then your third confirming ray comes straight through the center here because undeflected through that pathway, straight down. They find a meeting point in this spot. Your object distance is P1. Your image distance is going to be Q1. You want to check your tables to make sure that you keep your signs correct for what those values actually are once you've measured the lengths. And so you draw your image for your first lens in this position. Now this first image becomes your second object, object 2 for your second lens. So now we've got this point here, and that position is P2. So now you begin your ray diagram. Now one thing that you'll notice is I've actually got my colors kind of funky here, and I apologize about that. But you still follow the same rules. You go horizontal to the axis, bend at your lens, at the axis of your lens, towards the focal point on the opposite side. And in this case, it kind of goes off this way. But when you do your second one, which goes way down this way, off the board in this case, because I guess I overdid it with my dimensions, comes off the side here, and then it's going to refract. If it refracts this way, these are never going to combine. So we know the image is not going to be over on this side. So we have to backtrack these, and they backtrack, as you can see, still off the board because the image is going to be very large. And that's our goal with a microscope. We want a really big magnification, so it's going to be very large. And then for our third beam, we have our confirming beam, this third beam here, which we would direct through here. Again, you can see that they're going to diverge. And since they're going to diverge this way, we backtrack, and you see that they are headed to converge at the same spot. Now this is clearly too big for this board. Things happen, but we're trying to keep it reasonable on your paper, and the best way to manage that is to have your height of your object to be smaller. You make it a little bit shorter. So play with a few things, make sure you draw lightly before you make everything more firm. Distance Q2 is on the same side as your object 2. And so this should be negative if you double check your tables. This should be negative. So when you plug that into your value, this negative is the negative of this ratio. This Q2 or this Q1 may be negative itself, and flip your signs around. So just tread carefully with that. So finally, you have this enlarged image that you draw from the axis down to your convergence point. You can measure the height of that, you can measure the Q of that in this case, and determine what the magnification is. You can also look at the formulas that are in your lab manual to use alternate methods to get that value. The alternate ways that you use in your lab manual may include the variable L, which is the length between your two lenses. So there's a couple ways for you to make this calculation, where this will be the focal point 1 will be focal point of your object, F sub O, and F2 will be your focal point of your eyepiece, this is F sub E. This is a simple combination of two lenses. Many microscopes and many telescopes use more than just the two key lenses in order to maximize certain features about optics. But for today, hopefully you'll come away with a better understanding of the ray optics and how that plays together in multiple combinations. Okay, so in this week's lab, we're going to be working with optical components, and we'll be using them on a whiteboard that is also magnetized. You can wipe away the whiteboard marking. In order to work with this, you'll need a laser source, and so we've got this laser optics box, laser ray box, and you can magnetize that, and you can see that it doesn't slide off. The magnetic field is pretty strong on it, and your best bet is to move it up against the edge so that it's flush against the edge and has a nice square shape to it for the laser beam to go with it. When you put on the power, it creates the laser beams that, can you see those? Barely can see on this, but the lights will be dimmed in the class, and then you can take a look at that. Each lab station is complete with several magnetic surfaces that have images drawn onto them. For example, you lay this onto the surface, and if we turn the lights down, and when we dim the lights, you can see that the magnetic surface stays nice and affixed to this. We can slide it around to make sure that the center line aligns with the center beam. Once you're reasonably satisfied that that beam is nice and aligned and your surface is flattened out, you can take one of the optics that are given to you and put them into place and make measurements and follow the instructions that are given in your lab guide. One of your first steps is going to be finding out what the focal length is for each of these optical components that are in the lab box. Once you figure that out, you'll move on to the next step. This is a very simple lab, and it's probably going to go pretty quickly for you. So there's not much else to show you except for that these stick to the surface and they're very nicely laid out, and that you'll be having whiteboard markers next to you so that you can make adjustments as needed. This week's lab report style is going to be the worksheet style, so you want to submit the worksheet with a summary at the back. Remember, you take a little time to talk about the theory a little bit, the combination of magnifications. Talk a little bit in your summary about if your career is going to involve the use of microscopes or any other lens combination situation. You want to talk a little bit about that in your lab summary. It's important to be aware that something coming up, now that you guys have finished the optics sequence, you want to be aware of something called the scanning electron microscope, which you can see here. The scanning electron microscope is very similar to an optical microscope in the fact that it does use bending of beams and rays in order to form an image, but in this case it uses electric fields to bend beams of electrons to get higher resolution, because the electron is much smaller than the size of an atom, whereas light is on the order of the size of an electron and makes a very poor optical sensor. For example, if you take a piece of fabric and you run your fingertip over top of it, or maybe the corner of your phone, you may or may not notice the wedges, the little contours between the lines of the woven fabric. However, if you take a pin, the needle of a pin, and drag it over that same surface, you should start to notice a much different texture. Well, that does it again for this week's walkthrough. I hope that you have a better understanding of optical instruments and optical instruments in your practical use. If you have any questions, you can always ask your TA, you can ask me, you can ask your classmates. You can also stop by the Physics Help Center. The Physics Help Center is there to help you be more successful in physics, and sometimes it's not about getting the help, it's just being around other people who are doing the same basic work that you are. So give it a try if you haven't already. And now, Captain, we'll see you in the laboratory. All right, everybody, welcome to another week's walk. First take. Try that again. Oh, Captain, we have a ship off the starboard bow. Terrible. Okay. Oi, Captain! There's a ship off the starboard bow! Oh. Don't do that again. Optics.